The gas laws we're going to go over, there are two of them, Charles's law and Boyle's law, and they are related to gases. That's important. Step number one. Realize we're thinking only about gases, like the air in this room, not liquids, not solids, gas laws. Charles's law talks about how volume and temperature are related, and you probably already know this answer. Jordan, think of a ball left like outside or in your garage or something when the weather gets colder, like a basketball left in a cold garage. What happens to the basketball? What happens to the volume of the basketball? Jordan. You never notice this? Left the ball outside in the cold.
Doesn't it, like, the volume?
There you go. It's going to decrease. So if the temperature decreases, like a basketball left in a cold garage, the volume will decrease. It's not that the basketball lost air. It's not that it has a hole in it. It's that the volume decreased inside. Another important point, when we're going over the gas laws, please don't assume we're either adding air or removing air. There's not going to be a leak in the system we're talking about. With basketball, it's a closed system. I'm just talking about that set amount of air in the basketball. Okay, and then vice versa, the temperature increases. So if you've got a basketball in a hot garage, will increase too.
Will the air expand?
Exactly. And there's a formula for that. The ratio, like the cold ratio should equal the hot ratio. And to use this formula, we really just have to make sure that our temperature volume units. But V1 and T1 will be volume and temperature. Volume and temperature finally. It will decrease. Basketball left in a cold garage. Not that there's a hole in the ball.
Will it really be like flat?
It seems like it's flat. It might look a little flat, might feel flat, but it isn't because it lost air. It's simply because the temperature decreased.
So when it gets hot, it'll blow back up.
Yeah,
Yes.
If I let a completely flat basketball in a hot garage, I come back the next day, it will be like.
Not that big of air.
It will be more full than it was. Like
Hold on, so
the volume will increase. How much it will increase, I can't say, but it will increase.
what about it?
So here is a problem related to Charles's law. And I like to think Charles's law starts with a C. Celsius starts with a C. That's the one that relates to temperature. But here's a math problem for us. So, a fully inflated basketball has a volume of 2.5 liters at a temperature of 203 Kelvin. No. It's actually cold. The relation between Kelvin and Celsius is 273. So 273 Kelvin is actually 0 Celsius. So this is the freezing point of water. So this is cold. What's the volume of the same basketball at a temperature of 293 Kelvin? Okay, so 293 minus 73, that's 20 degrees Celsius, which is really just about room temperature. So we're going from the freezing point of water, so we're going from like 32 degrees Fahrenheit to about 70 degrees Fahrenheit. So this is, a different temperature unit. And we will use Kelvin for these problems. Oh, and the reason actually why we do need to use Kelvin, little side note on Kelvin, is that Kelvin's never what? Any guesses?
Wrong.
That other temperature scales will be.
It's never too big.
Wrong. Too small.
It's never too small, meaning it's never negative. It's never negative. So we don't want to, ever end up with like negative volumes. So we're going to stick with a temperature scale that starts at 0 and just goes up. Because 0 Kelvin is called Absolute zero. So it's like the coldest possible theoretical temperature. All right, so anyway, we are going to use Kelvin because Kelvin's never going to be negative. So don't be confused with the K. It's just a different temperature scale. So start by setting the formula. I see temperature involved, so it's going to be Charles's law. I look for my word. Here's my what is the volume. But now I got to be just a little careful. Do I want volume 1 or volume 2? Yeah, I want volume 2. So you are going to have to think about that a little bit. Do you want the initial situation, the final situation? I want volume 2. So the thing I want, just leave as you. Everything else I should be able to plug in. So Mason, can you tell me what volume 1 should be? 5. Yeah, and as far as the units go, well, I'll be liters for the time being. I'll talk about that in just a second. Hannah, how about temperature 1? Good. That was to 273, which means temperature 2 has to be the 293. So we've done a little bit of rearranging with the density problems. Just back to math class. What do you do? Cross multiply first. And these are all, any of the fraction ones, you're going to want to do that. I don't know what 2.5 times 293 is. Thank you.
I don't know which one. About.
Whoops.
It's about 273 squared.
Okay, so I multiplied. And go ahead, Chase. What do I do next? Bye. Yeah, we're trying to get B2 alone, so divide by 273. 2.7? Thank you. All right, now back to the units issue. What unit? Liters. And this is where you have to look back at what you started with. If we started with liters, then our final unit should be in liters. And there you go. There's one of the laws. That was, again, Charles's law, the temperature law. Okay. Our next gas law deals with pressure. So first we need to have a sort of understanding of what pressure means. Pressure is a unit of force acting on a unit of area. So I'm wearing sneakers. All of my weight is acting on my little feet area. But could be wearing high heels. These are some tall. In which case all of my weight would be acting on a smaller area, just here and here. So the bigger the force, smaller the area, the smaller this little area, the greater the pressure. So high heels versus sneakers, there'd be the same force, it's still the person's weight, but there's different what's? Areas, thus making different pressures. And here are a few units of pressure that we'll see. In the English, we got pounds per square inch. PSI, probably heard of that. Maybe you've heard of atmospheric pressure. We're all under one atmospheric pressure now. ATM. Any guess what mmHg refers to? How that works? It's millimeters of mercury. It's sort of how barometers work. Where's my little... if you imagine, I don't know, some container that had a whole bunch of mercury in it, and then you just had a little glass tube. The more pressure, more atmospheric pressure down on the mercury trace. Will you just scoot up a little bit? Okay, you guys should be good, right? The more pressure acting on the mercury, what happens to the mercury in the tube? It rises, it would go up. Okay, so that's another system of measuring pressure. Meters of mercury. There's a whole bunch of bad things that can happen if you do high heels all the time. One last explanation of pressure. On the microscopic level, you can think about pressure as how often the particles hit the sides of the container. And, yeah, I did, but, yeah. Temperature also does affect pressure. Hot, from our kinetic theory, those particles are going to be moving around faster, the size of the container more and more, so that would be under pressure. So think about how often the particles in the container are hitting the wall. If for some reason they're hitting frequently, that would be high pressure. All right. So this is Boyle's law. Remember this one. Kerr's law. The volume and pressure of a gas are indirectly related. So what would indirectly mean? Opposite. If the pressure increases, it was because the volume decreased.
Is that not the same as the other one?
The other one was opposite. The other one was the same. This one is opposite. Temperature goes down, volume goes down. Here, pressure goes up if volume goes down. And this is your Boyle's law formula. P1V1 equals P2V2, so no fractions in this one. If you pump the same amount of air into a large beach ball and a small beach ball, which ball is under great pressure? The small one. And this is only a valid comparison if I'm talking about the same amount of air. All right, here's sort of another visual of that. Picture obviously represents the biggest volume of gas. The first one, and maybe this is a car pushing down, adding some gas, but okay. Big volume. What would you say about the pressure? Yeah, low pressure, not a lot of pressure here. Here, little volume, a lot of pressure. So, imagine we're in this room and it's totally sealed off, and it's like one of those old Indiana Jones movies. And the ceiling's coming down, and there's spikes. Has anyone ever seen that movie? Okay. So, if the ceiling's coming down on us, what is happening to the volume of air in this room? Assuming it's like sealed off. Okay, the volume's getting smaller. Therefore, what's happening to the pressure in the room? It's getting bigger. It's the same amount of air, but if I'm squishing it down to a small volume, it's definitely going to be hitting the sides, of the walls and the ceiling, the floor more frequently, so it's definitely going to have a greater pressure. So just think of them as opposites. Big volume, small pressure. Small volume, big pressure. What? Yes?
We wouldn't be able to tell that.
You wouldn't be able to tell?
We'd start moving from our neck.
Like if you couldn't see the ceiling coming down?
No.
You actually would.
It sounds.
Yeah, you probably would feel it in your ears first. You ever been on a flight too? Up in the air? Or when you swim to the bottom of a pool. That would be a high pressure example. Yeah, you could probably feel it. Okay, this one. It says if a small child sits on a beach ball, decreases volume 5 meters cubed, what is the pressure inside the ball if it was originally at 1 atmosphere pressure and 0.6 meters cubed? Okay, so here's the question word. Blake, what are we even trying to find? Okay, and with pressure, the first one or the second one? Yeah. How do you? Okay, you gotta read it carefully. Here's your one information. It says, what's the pressure inside the ball if it was originally at all of this at 1 sphere pressure 6 meters? So you do need to read them carefully, because if you switch the ones and twos, that's definitely gonna mess you up. But that's all your original like one info. So 1 atmosphere of pressure, okay, so that's P1. So it's got 1 times the 0.6, the original volume. And my units match, and I will not try to trick you with units here. So this is fine. P2 is what I want. And V2 is 0.5. Okay, so we get it all set up. And I can actually go ahead and kind of simplify and decide what's 1 times 0.6. And, you know, these ones and twos, like, don't think the 2 means you got to divide by 2 or do anything with the 2 at all. It's just saying it's the second pressure. Don't try to square anything. So we kind of simplify down to that. And our last step would be to divide by 5. And then 1.2 what? Yeah, you've got to look at the unit you started with for pressure. So it should be 1.2 atmospheres, ATM. And try to, like, double check and make sure your answer makes sense. Make sure you didn't switch the numbers, because, I mean, if the person is sitting on the ball, should the pressure go up or down? Up. So you've got to know your answer is bigger than the original pressure. It should make sense that it's bigger than 1.